Hello and welcome to the second half of the video lecture in which we're going to talk about thermal energy and then we're going to talk about work and power. So thermal energy. Thermal energy is the sum of kinetic and potential energy of the particles in an object. So thermal energy increases as mass increases. And so the reason for this is that we know that kinetic energy, the component of that is mass. So when mass goes up, the kinetic energy is going to go up. That is 1/2 m times velocity squared. And let's see. Okay, thermal energy increases as temperature increases. So that seems kind of straightforward, that the amount of thermal energy is going to increase as the temperature goes up. So when mass increases, thermal energy goes up, and when temperature increases, thermal energy goes up. What is temperature? Temperature is a measure of the average kinetic energy of particles in an object. And now we know that kinetic energy is related to movement, and we know that things that have a higher temperature, the particles are moving faster. We talked about that in chemistry. So it would make sense that temperature would be a measure of the average kinetic energy of particles. Things that are very warm, the particles are going to be moving very quickly, and things that are not as warm are going to be moving slower. So the higher the temperature, the faster the particles are moving. And so now we're going to talk about heat. And so think for a minute, how do you know if someone has been sitting in your chair in the classroom? So if you come in from the classroom and you sit down in your chair, how do you know if somebody was sitting there before? And so if your chair feels warm, you know that somebody has been sitting there before. But if your chair feels cooler, then you can imagine that somebody probably has not. We'll talk in a minute about the concept of something feeling cold and how there actually is no real cold. It's just an absence of heat, but we'll get to that in a minute. So thermal energy always flows from higher temperature objects to lower temperature objects. So the reason that your chair feels warm if there was somebody sitting there before is because that thermal energy has flowed from that person's body. So heat has left that person's body and it has flowed into the chair because your body is going to be warmer than the chair because your body is generating heat. So heat. Heat in physics is designated by an uppercase Q. Why that is, I could not tell you. But it is Q, and it is the transfer of energy from one object to another. We are always going to go from a higher energy object to one with lower energy. So that is always the direction in which energy is going to flow. That is always the direction in which heat is going to flow. So because heat is a measure of energy, we measure it in joules. And now let's talk about the transfer of thermal energy. So there, as I kind of mentioned in the last slide, there is no such thing as cold. When you feel cold, you are simply feeling the absence of heat. So what do we mean by that? If you think about this example, explain what happens when you hold a cold drink and your hand starts to feel cold. So if it's a really hot summer day and you've got a nice cold can of Coke or Mountain Dew or whatever it is that you like to drink, what happens if you hold it in your hand after a while? Well, after a while, your hand is going to feel really cold, especially if it's really warm out. You feel like, oh, that's a real contrast to feel cold. And if you hold it for a while, condensation starts to appear on the outside of the can. And that is actually not because your hand feels cold, but because heat is leaving your hand. It's going from that area of higher energy, higher heat, into that cold can. The reason that condensation appears on the outside is because that heat is actually going into the can and it's causing the water to condense on the outside. When heat flows into an object, the change in heat is positive. So when heat is coming in, energy is coming in, and the change is positive. When heat flows out of an object, the change in heat is negative. And unfortunately, I can't move my little doodad here. Here, maybe we can do it this way. There we go. So when heat flows out of an object, the change in heat is negative. So when heat is going out, heat is leaving, there is less heat, the change in heat is negative. There are three ways that this transfer of thermal energy can occur. The first one is conduction. Now, usually when we think of conduction, we're usually thinking in terms of electricity, if something is a good conductor, but we're really talking about whether it is a good way to transfer energy of any kind, and in this case, thermal energy. So conduction is transfer energy through matter by direct contact of particles. The particles are actually coming in contact with one another, and that is how they are transferring that energy. Solids are the best conductors of heat. Why is this? Well, if we think about how are particles arranged in a solid as opposed to a gas or a liquid, we know that in a solid, the particles are the closest together. In a liquid, they're a little bit further apart. And in a gas, they're much further apart. So solids are the best conductors of heat because the particles are already so close together, contact is really easy. They don't have that far to go, and many of them are already touching one another. The next way that we transfer thermal energy is something called convection. You may have heard of a convection oven. Convection is the transfer of energy by the movement of heated particles. So I'm going to minimize myself again. So in this picture of this tea kettle, we're seeing an example of convection. Convection occurs in liquids and in gases. Currents move the heat from warmer to cooler parts of the substance. So when you heat a kettle on the bottom of the kettle is coming in contact with a hot stove, and the water that is warm, we know that heat rises. So that warm water on the bottom is actually creating a current that is going to move towards the top of the tea kettle. And when it does that, it's going to take this quantity of colder water and push it down towards that hotter part on the bottom that's making contact. So if you were able to actually view the current within the kettle, it would actually be the water would be cycling because the warm water would be moving up. It's going to push that cold water down, and that cold water is going to heat, and it's going to continue until eventually it's going to boil, it's going to whistle, and you're going to take it off of the stove. So that's an example of convection. The same thing happens in a room that is being heated by hot air. So if you blow hot air into the bottom of the room, that heat is going to rise, and it's going to rise to the top of the room. And as it rises to the top of the room, it is going to force out that cold air to come down. That's why sometimes when you're heating a room, you might turn on a ceiling fan, which seems kind of counterintuitive in the wintertime, but what you're actually trying to do is take that hot air and force it back down so that you can enjoy that heat and that you're not constantly cycling that cooler air down. The last way that we transfer thermal energy is radiation. So that's transfer of energy through electromagnetic waves. This occurs fastest in gases. It can be absorbed or reflected, and it can travel through space and between molecules. So you think about radiation, we know that we hear about radiation from the sun in terms of UV rays and how that's harmful to skin and sunscreen and that whole argument. But radiation also, when you feel that warm sun, that is energy being transferred through the sun through electromagnetic waves. So we know that when we're outside and we feel energy, radiant energy from the sun, that's traveling through the gas that makes up our atmosphere. We can absorb some of that heat, which we do. It could also be reflected. So you could have certain materials are very good reflectors of radiant energy. Some metals. So if you were to, for example, some in the south here where things are very warm and the sun is very strong in the summertime, there are certain roofing materials that are designed to reflect that heat so that that heat's not absorbed by the house and you're not killed with a really high power bill from running the AC all the time. This radiation can travel through space and between molecules. So it is able to penetrate some of those, even if it's a solid material, it's able to penetrate some of them, and so you'll still get some radiant heat from the sun no matter what the roof is made out of. So now we're going to talk about how some materials transfer heat well and others do not. So when something is a conductor, it's a material that allows heat to flow easily. So when we think about things that are made to use heat, like pots and pans, or pipes that carry hot water and things like that. So metal, usually most pots and pans are made of metal. Things that we want to conduct electricity are made of metal. But one thing that we may not necessarily think of as a conductor is skin. So think about this, when you hug one of your friends in the wintertime and you're both bundled up with coats, you're probably not going to feel a lot of transfer of energy between you and that person because there's not a lot of skin to skin contact. You're usually wearing, long sleeves or a winter coat or gloves and things like that. But if you hug that same person in the summertime, even if you're in an air conditioned room, so if we take the temperature, the outside temperature out of the equation and just consider the fact that in the summertime, usually you're wearing short sleeves and shorts and things like that. When you go to hug that person, the areas where your skin touches, or even if you're holding your sweetheart's hand, you're going to feel that heat transferred from that person, and that's because skin is a very good conductor of heat. Insulators are materials that do not allow heat to flow easily. So think about in the summertime, your cooler, so your Yeti or whatever other kind of cooler that you have, that's made of insulating material so that your ice stays frozen and you're able to keep your drinks cold, or your game that you've been hunting or anything else that you're going to throw in a cooler. Air is a good insulator. Wood is a good insulator. Styrofoam, which is of course the material that's in some most coolers, plastic, and also fiberglass is an insulator. So typically if we want something to conduct heat, like we want to cook something or we want to transfer heat from one place to another, we need a conductor. If we do not want heat to escape, or excuse me, to penetrate something, we're going to use something that is an insulator. All right, so we're going to talk about specific heat. This is probably, it's not a hard equation, but it's the one with the most variables. And it's specific heat refers to the amount of heat needed to raise the temperature of 1 kilogram of a material by 1 degree Celsius or Kelvin. Now, the very first thing I want you to take notice of is that we do not typically here in the United States use Celsius or Kelvin as our measure of heat. The rest of the world does. We usually use Fahrenheit, so we need to make sure that if we start with a problem that has Fahrenheit, that we're converting it to Celsius or Kelvin. That is not a difficult equation. That is something that you can reasonably be expected to do in this course. So I want you to push yourselves. And if I give you the formula to transfer it, you should be able to do that. So this is specific to different types of materials. So there is a set number for specific heat for each material. So that is not something that we calculate, that is something that has already been determined. The specific heat of tin is always going to be the same. The specific heat of copper or gold or any other conductor is going to be the same. It doesn't matter if it's here or there. Anytime you have gold, it has a certain specific heat. We measure specific heat with something called a calorimeter because class is not in session right now where you're not able to play with those, and that is really unfortunate. So maybe if we are back at the end of the year and we have time to do that, we can, because those are kind of fun. But that is how we would determine specific heat if we did not know beforehand. But for the purpose of this lesson, we're going to be presented with situations in which we know what the specific heat is. So this is the specific heat equation. So Q, we remember, is the measure of heat energy, equals MC delta T. And so this little triangle here, we refer to that as delta. You may have run across that in math before. And so anytime we see delta, that is a change in temperature. Well, this is delta T, so change in temperature, but a delta is significant of a change in anything. So we have Q equals the change in thermal energy or heat, and that's measured in joules. We have M is the mass, and that's going to be in kilograms. Let me minimize myself again. We have C here, that is the specific heat. That is something that is known, and that's measured in joules per kilogram per degree Celsius. And delta T is change in temperature. So how do we calculate the change in temperature? The change in temperature is the final temperature minus the initial temperature. So this is a lot like when we were talking about the change in velocity when we were calculating acceleration. So delta T, change in temperature, you're going to identify in any problem the final temperature and then the initial temperature, and is the difference between those. It is very important that you put these two things in the correct order, because if you put them in the reverse order, your answer is not going to come out correct. And that is measured in degrees Celsius. All right, so let us do a practice problem. A wooden block has a mass of 20 kilograms and a specific heat of 1700 joules per kilogram per degree Celsius. Find the change in thermal energy of the block as it warms from 15 degrees Celsius to 25 degrees Celsius. So just as we do for any other problem, first we're going to list out what is known. We are given that the mass is 20 kilograms. We are given that, all right, sorry guys. We are given that the specific heat is, I got thrown off because that should be a lowercase c, but it's kind of hard to tell against the other letters, is 1700 joules per kilogram per Celsius. We are given the initial temperature as 15 degrees and the final temperature as 25 degrees. We are being asked for Q, which is the change in thermal energy or the measure of heat. So we know our equation is Q equals M times C times delta T, or the change in temperature. So we are given all of the variables. We know what we are looking for has already been isolated, so we're just ready to go. So delta T, we remember we are going to take the final temperature and we are going to subtract the initial temperature. So you want to make very sure you know which one is the initial, what is the temperature that you start with, and what is the final temperature. So we're going to plug this in. So Q equals 20 times 1700 times 25 minus 15. You want to be very sure that you are following the order of operations so that you get the correct answer. So you're first going to subtract 15 from 25, which reduces down to 10, and then you can just multiply these out. So you're going to get 340,000 joules. That is going to be the change in energy of the block as it warms from 15 degrees to 25 degrees. Okay, so I'm going to give you this practice problem. You're going to use the equation that you were given. Go ahead and try to work this out. Go ahead and pause the video and do that, and then I will show you the answer, and you can check that against what you have. Okay, so the answer that you should have gotten is 306,000 joules. If we have questions on how we got that, these are very straightforward. If you have questions on how to get that, please do either drop something in the comments section or send me an email, and I can post a follow-up video where we work this problem and some additional problems. All right, and now the last concept that we'll cover for our test coming up is work. So I love to ask, and unfortunately I can't get a direct response from you guys, have you done any work today? How would you define work? So there is actually a scientific definition for work. And we define work as the transfer of energy that occurs when a force makes an object move. And that move word is really essential for the definition of work. So when we're talking about work, we're using an uppercase W. And as you can tell, as we get further into our study of physics and these equations, there are a lot of variables and they are designated by a lot of different letters. And so if you were taking a full-blown physics course, by the end of the year you would have a notebook full of variables, their abbreviations, and equations. So as we get further into this, as we were starting this, you might say, okay, well, I'm going to be able to remember this, I'm going to commit it to memory. I would really recommend just set aside a page in your notebook to write these formulas down, and that way you always have that to reference as you go through the year. So not necessarily for this class, but for if you're in a year-long chemistry class or year-long physics class. Okay, we measure work in joules. So you're noticing a pattern. Anything that has to do with energy, we are going to measure in joules. In order to do any work, you have to meet two conditions. The object must move, and force must be applied in the direction of the movement. So in order for this stick figure to be doing work on these books, the books would have to move. If the books are staying stationary in place, no work is being done. The object must move and force must be applied in the direction of the movement. Work can be summarized as an equation, and it's a very simple one. Work equals force times displacement, and we recall from our earlier lessons that displacement is the change in location. So if I start at my table here and I get up and I walk 2 feet to my right, my displacement is 3 feet. I started at the table, I finished 3 feet away. That is a displacement of 3 feet. Okay. So work is a capital W, we measure that in joules. Force is a capital F, that is measured in newtons, and D equals distance or displacement, and that is going to be measured in meters. So example number 1, you move a 75 kilogram refrigerator 35 meters. This requires a force of 90 newtons. How much work in joules was done while moving the refrigerator? So what is the first thing that we are going to do? We are going to identify what is given, and we are going to identify what the question is asking for. We are given that the mass is 75 kilograms. We are given that the distance is 35 meters. The force is 90 newtons, and we are looking for work. But wait a second, our equation for work is force times distance. There is no mention of mass. Well, this is an equation, this is one of the word problems where you have to identify what information that you need and what information you do not need. So even though we are provided with the mass, we do not need that information. So we can just get rid of that. Beyond that, we know that the equation for work is W equals F times D. And we can just go ahead and plug and chug. So we're going to plug in 90 newtons for force. We're going to plug in 35 meters for distance. W equals 90 times 35. And we're going to get an answer of 3,150 joules. These are very straightforward. We can do some more practice with these if necessary. I think I've got one more slide. Let's see. Okay, so we've got 4 practice problems. Go ahead and pause the video and work through these. and then I will show the answer. Before I do that, I do want to say, please, if you have questions from this lecture, either drop a comment or send me an email at morin@gsicharter.com. Message me on Remind. If you have not joined Remind yet, please do so. It's going to make life so much easier for us as we continue through this extended learning. If I can speak to each one of you individually, email and dojo is kind of a nightmare. So please, if at all possible, join Remind. It's going to make everyone's life much easier. I know Ms. Dowling already uses it. So we're just kind of trying to fall in line together. Okay, so go ahead and work these problems and pause the video. And then when you finished, unpause the video and check your answers. And that's it for this video. I will see you guys in a follow-up video, hopefully later this week. Bye.